So welcome back. I will start also that part of the lecture with a question on Clicker. I would like to ask you a few things. In fact, already now. What do you think there is in a data center? You probably heard of data centers on television. Now it's all over the place that there are all these big companies with these gigantic data centers. What is there in a data center? What do you think? Is it top secret? Like this is just some place that does computations and brings LLMs alive? Or is it a really big machine with 1,000 core CPU, 100 petabyte disk and a petabyte of memory? Or is it plenty of small cheap machines? Or is it a giant quantum computer with an array of 54 qubits? I thought of Sycamore, but I think that one of the qubits failed and it went down to 53 in the real experiments, but 54 was the intent. Right, the votes are coming in. Right. You see what you say. There is a majority, and the majority is even correct. So it might be something very disappointing if you imagined or idealized what a data center is, but in fact, yes, it is just rooms filled with cheap machines. This is what it's about. Right? So cheap machines, some of them are basically can be pretty much like your laptop. But in fact, it's a slight exaggeration because the machines in the data center might be a bit more powerful than your laptops, but it's nowhere near a petabyte of memory or 100 petabyte of disk. In fact, that doesn't even exist. A petabyte of memory doesn't exist today. 100 petabyte of disk doesn't exist today. The only thing we know to do is plenty of machines with small amounts of memory, small disks, and so on. All right, so this is what there is, and I will tell you more in just a few minutes. But at least it demystifies probably for you what a data center is. Okay, so cloud storage. So what is on the agenda for this lecture? It's big data. So we need to query large amounts of data. What kind of data? One example is the data that we gather with experiments, like, for example, the Sloan Digital Sky Survey. I took a look at it, the phase 4 that lasts until 2020. And I tried to see how much data there is in there. And I found out that there is 273 terabytes of data. And it's organized in 680,000 directories with 176 million files. Right, that's a lot of data, but this is what we have in, and now we want to analyze it because this is data that can be queried with SQL, with other languages, in order to discover, I don't know, black holes, neutron stars, quasars, and so on. Now, the first question that arises is, how and where do we store that? Because that's a lot of data. Well, for sure, that will not fit on your laptop, right? So we need another way. Now, what do we have? We have relational databases, but the problem of the relational databases, at least in the early 2000s, is that a relational database system fits on one machine. So if you thought that you could just put these 200 terabytes in a relational database, think again. It just doesn't work because that's only one single machine. So that's not an option. And in fact, that's exactly what happened in the early 2000s, is that the companies ran out of options because the data that they needed just didn't fit anymore in the systems that we had. So we need another solution. Sorry, I have a delay. Whenever I click, somehow it takes a few seconds until the things appear. All right, but I have good news for you. I have good news is that everything that has happened in the past 50 years, since the 1970s, and if you want even earlier, can still be reused, even with the new technologies. So the notion of selection, projection, grouping, sorting, joining that I threw at you last week and this week will still apply. Languages, declarative, functional with optimizations, query plans, that's the Greek letters, indices, and so on, will still apply. We can still have that. What the table is made of, tables, rows, columns, primary keys, that also we will still see. But we might not have only that. We will expand to other concepts. But it means that a lot of what we've learned can be reused. That's a very, very good news. But there are things that will drop. And that shouldn't surprise you because I told you the normal forms, this is going away. So the second normal form, third normal form, Boyce code normal form, this is all going away. All you need to know for the purpose of that course is that a normal form is kind of the opposite of a join. A normal form means splitting the data, dropping the normal forms means that you put it back in a giant table. Tabular integrity, domain integrity, atomic integrity, this is basically what brings the tableness to a table, right? The fact that you have the same columns, values for the same columns in every rows. Within a column, all the data has the same type. You don't have a table in a table in a table. So everything that makes a table, we are throwing that away. And we'll see things that are not tables. Instead, we are going to see data that's heterogeneous, because it might be that you have in the same column data with different types. We are going to see data that is nested, tables in tables in tables, and we are going to see data that is denormalized, meaning that it's not in a high normal form, it's just a giant table that we are going to query. That beautiful word was known as a buzzword. It was a buzzword, now a little bit less, and that buzzword was NoSQL, not only SQL. And everybody was like NoSQL, NoSQL, NoSQL at the time. That was the ChatGPT of maybe 15 years ago. So this is actually what's going to be new, and we'll spend weeks on that. So what's going to happen in the coming weeks is that we'll have to rebuild the whole stack. What do I mean with that? Is that if you look at a relational database system, the good old ones of the 70s, they fit on a single machine. It's just a piece of software that you install. In fact, PostgreSQL is exactly that. It's like a black box. You just download it, install it, and that's it. Then you interact with it. We need to rebuild all of the components to break it apart and rebuild it layer after layer. It's like building a house. You have the foundations, you have the walls, the electricity, the plumbing, and so on, right? So we are going to do exactly that. Like we build a home, we are going to build the big data technology stack. So these are all the levels of the stack. We spend the entire semester doing that. The first level is the storage. That's what I'm telling you about today with the cloud storage. There's plenty of fancy technology names. It's where you put the data, basically. Then you have a level that's called the encoding. This is how you convert the data to zeros and ones. Not very relevant for that lecture. It's more like I'm mentioning it, but we don't actually spend too much time on it. You might have heard of UTF. Who heard of UTF-8? Okay. UTF-8, if you create text files, you should go for UTF-8. This is basically the way you get all the international, all the languages, and all the special characters to actually work, as opposed to ASCII or ISO 8859, that's for the European characters, but there's many others. UTF-8 today is the way to go. So this is how you encode it, but this is, again, we'll not spend too much time on that. Syntax is, how do you represent data as text that you can then store on your disk? Examples are XML, JSON, CSV. CSV, I'm sure you heard. Who heard about CSV? All right, it's all over the web. Whenever you can download data, it's going to have the CSV option, just a way to represent tables. It's table represented as text, right? XML, JSON, that's trees represented as text. RDF, XML, turtles, that's graphs represented as text. And XBRL, it's cubes represented as text. So this is all syntax to store data as text. Why? Because you want to transmit it over the web. You want to download it and so on. So this is why we need syntax. Then we have, if my computer would be so kind, yeah. So we have data models, which is how you model the data. So in the case of tables, that's rows, columns, and so on that I told you last week. For trees, we will see that. Graphs, cubes, it's not in that course, but it's basically just the model behind the data, the representation of your data, right, that you then manipulate. Then there is validation. Validation is the process of putting constraints on the structure of the data. For example, the fact that in a column, all the values are strings or all the values are dates and so on, this is validation. That's something we don't hear about in relational database systems like PostgreSQL, just because it's mandatory. You cannot even start working with data if you don't already have a schema that ensures that the data is structured. But we'll see that in big data, we actually make it optional rather than mandatory, and so it appears a bit more explicitly. So we spend a whole week doing that. Processing the data is when the data, that's the best part of the lecture. It's when the data flows in the data center across thousands of machines and just in a way that delivers the result at the end. So this is my favorite part. So we look at MapReduce and Apache Spark. Then indices that can be very convenient to very quickly looking up data. I tell you all about that again in a special week. Then we have the data store. So here it starts looking like a product that you sell to people, right? So a data store is basically a technology, and you might have heard some names here. MongoDB, who heard MongoDB? Right, this is now almost becoming, it was already a buzzword years ago, but now I hear people again talk about this. It's a database company that is selling a NoSQL product based on trees. Couchbase, Elasticsearch, it's all based on trees as well. Hive based on cubes. HBase, that's a big table. That's actually the open source version of Google's big table. MarkLogic is also a NoSQL product. Cassandra would be Meta or Facebook's alternative to HBase and so on. So this is called the data store. This is basically what you sell or put for people to download and use. That's the wrapper of everything else. And then the top that you can achieve on top of a data store is if you have a real query language. Like SQL, there are others for other shapes. But when you have a query language, you are basically making the user's life much easier because they can use that language to query the data. And finally, the ultimate level, and you can have user interfaces. And in fact, I forgot to add it, but this is where you put the LLMs and ChatGPT and so on, like the natural language interface that is going to be part of the ecosystem as well. But that will not be part of the lecture, but just so you know that it is in there. And in fact, since ChatGPT is so good at writing SQL, then you can imagine that it can actually be of help for people who don't know SQL. Right. So this is the stack. It's one semester's worth of work here. So we need to start somewhere, of course, and this is why today we just start at the bottom of the stack with the storage. So as I told you, we need to store the data somewhere, in particular this astrophysics data, for example. So there is always a storage level. In fact, I hear a lot from physicists that information is physical. So whatever information you have must be in the end with atoms and molecules somewhere. But we need to figure out where. I can click again, but then it's going to go by 2. Oh, okay. Now, here's a very important point to understand. That's absolutely fundamental. There are 2 kinds of systems, 2 kinds. One kind of system is like PostgreSQL. It's basically a system that is monolithic that handles everything for you, right? So it means that you need to import the data in it, and then it's going to figure out how to store it all by itself and how to query the data and so on. That's called ETL. So these are the traditional databases, right? It's really just a closed system, and you can only interact from outside. What it means is that it's hiding the complexity from you, but it also means you cannot see inside. But in the 2000s, something emerged, or it would be more precise to say re-emerged, because that's actually pretty much how it was in the 60s, but in some cases, this is what you need. That's called the data lake. A data lake is some sort of file system with directories and files, and you just drop your data in there as files. But the difference with the one on the left is that you see the files. You see the directories, you see the files, you can copy them over, download them, put them on the internet, and so on. So you actually read files from a file system. That's also called in situ because you basically query the data from where it is. So what you will have in there is CSV files, the JSON files, XML files, and so on, so all kinds of files. And you probably heard of these buzzwords, like when you sit in front of a Python notebook using NumPy, Pandas, Scikit, and so on, then typically you are working with a data lake, right? In fact, for some use cases, it's great, right? But you need to know that it's not the only thing in town, right? There are the systems that hide everything from you and you don't even see any files because that's all hidden. It's highly optimized. And then there are the systems called data lakes. For whom is the difference clear? Okay. So now we are actually focusing on data lakes for today, but the data lakes in the cloud, not just on your laptop. Now, if you start from the 70s, if we wanted to store things on a single disk, this is a hard drive. Already, I think you probably saw that already, right? This is what a hard drive looks like. Who never saw that? Okay, most of you saw it. Okay, so that's a hard drive. It has a rotating part here, a mechanical drive. These are the cheaper ones that we still like to use today. The files there are organized in a hierarchy. You can have directories and files in there. And moreover, the files are actually split in blocks. So if you have a file on your laptop, all these laptops right there, you might have files that are a few megabytes, let's say. They are not stored just as a megabyte on disk. In fact, the laptop is splitting them into 4 kilobytes blocks, 4 kilobyte blocks, a lot of these blocks, and it's stored block by block on your disk. Whenever you read or you write, it's block by block. So this is called block storage, roughly 4 kilobytes for your laptops, the data in there. Now, if you use that local storage and thought that you can squeeze the astrophysics data sets if you hit it strong enough with a hammer, then you're wrong. Because this kind of storage with the hard drives, it's going to work on a local machine. It's going to work maybe with your local network. Maybe some of you have at home a hard drive that you access remotely, right? But it's not going to work if 1 million people are going to connect to it remotely. It only works because it's just you, right? WAN is a wide area network. This is where things start breaking, right? And in terms of the number of files too, I don't know if some of you did backups. So if you do backups, you see the number of files. You might have thousands of files, maybe millions of files. You surely do not have billions of files on your laptop because this is also breaking the boundaries of what we have. But the problem is that for big data, we do need that kind of numbers. Right? So how do we solve that? With cloud storage, and this is what we see right after the break at 9:15.